recording started. And I'll go back and check the recording from time to time because, I think something is not reliable here. It could be my cable, it could be the USB connector, but sometimes, the drive just drops out entirely. So I'll have to check that occasionally. All right, so let's see. Did you guys get my spam email this morning?
Yes.
Some of you did? Okay, so I'll just go over one or two of those things, that I think is kind of particularly interesting, and then we'll go and continue with the class. Robotic News is really just a magazine. This is just a link to the website. And it's nothing really deep. There are no research paper here. It's really just the IEEE trying to let people know of what we are now doing with robotics. Yep.
So is NASA now shut down?
Sorry?
Is NASA now shut down?
Yep.
Shut down?
It's the government shutdown.
Yeah.
And yeah, it is.
NASA is.
What kind of shutdown was?
Like
There's a government shutdown going on right now,
Oh, okay.
which includes NASA.
Okay. What about the IRS?
That's probably us defining us as essential.
Yeah, because IRS actually makes, quote unquote, makes money, right? It actually brings money in, so they cannot shut it down. It's just like the Board of Equalization and also Franchise Tax Board as a state government. Those two branches, they would not shut down because if they shut that down, they stop the incoming stream. So that would be worse, right? And there are other departments too, like the Waste Management Board, which basically manages, how garbage is disposed and whatnot. That is also an income stream because they actually collect money from these collection stations. Okay, so that's why certain departments will never get shut down, and NASA probably does not bring in money, at least not yet. Okay, until we start to mine, other planets and actually get something coming, But I think it's interesting how they decide which department to shut down. But anyway, this is really just the size of the screen doesn't match on screen. So let me see if I can fix that first.
Yeah, they make money off all that research. That trickles in.
They make some, but not a whole lot.
Don't they get a lot
I don't know about
of just
that
like
one.
grants and donations and stuff? Or is it strictly?
That would be defined as revenue.
Well, the resolution is right, but it's not. Okay, let me change. There you go. Okay, so it was just because of the refresh rate is off. The screen just doesn't pick that up. Okay, so that's it's really just a show of different things, and there are all different aspects of robotics. Robotic boat attempt, Atlantic crossing. This one has been coming a long time. Boston Dynamics building bulletproof robot mule. It's basically a four-legged robot that can go over all kinds of terrains because it's not based on rotation. It's not based on a wheel, so it can easily go over like pieces of rocks and stuff like that. And they kept improving that.
So you could like dress it up as a cow and it could be like a spy or something.
I don't know. Suppose you can ram. You can put a ram on it too, so you can ram things like that. And no pun intended, right? And then you have Tesla Motors developing autonomous cars. I think I might have mentioned that already in this class. By year 2020, they're expecting dealerships to have cars that are fully autonomous that people can actually buy. The technology is already here. It has been here since 2009, Google Cars, okay? It's just that it's too expensive and it takes too much work to maintain and service those cars, and also there's the liability issue, and that's why it's not for sale at a dealership. But by year 2020, which is only 7 years away, think about it, 7 years away, people are expecting that we'll have cars on sale in a car lot that are fully autonomous. And I think it's going to be sooner. I don't think it will take 7 more years. I think it's going to be sooner than 2020. And the first cars that will be like that will be fleets of taxi cabs, because that makes sense, right? I mean, that really just makes sense. And also cars for rental in San Francisco and other area like that. It also makes perfect sense because you don't want to own a car because otherwise you need in a garage, you need a place to park, and so on and so forth. So you want to basically join a co-op of something, and then you just have these cars circulating on the street, and then you can just call on one and say, okay, I need transportation. Yep.
What do you think about freight vehicles too?
Freight vehicles.
Autonomous freight vehicles.
That may be a little bit out because those cars have to deal with a lot of emergencies. So
Okay.
most of the time you need a person on it, just in case something happens. But you can still navigate. The navigation part can still be autonomous, so that whoever's on the car can basically get some sleep or get some rest as the car drives itself. So that would actually be a good thing because I think the computer can make it even safer, because now the computer can have access to radar and lidar and other types of technology to understand the road condition, the distance to the car in front, in all kinds of different types of weather condition and stuff like that. So I think that's coming because it's not because it is high tech and it's cool. It's because it makes sense and it saves money for some people. And that's the reason why it will get here sooner than 2020, because some companies can potentially save a lot of money by making things autonomous. This also kind of rings a bell because when I was at the show, Korea GPS, one high school girl approached and then she was really quiet too, and I said, so are you interested in computer science? No. So what do you want to do, after high school? I want to be an Air Force pilot. And then I just had to, hand it to her, and I said, well, I'm sorry, but I'm afraid by the time you're done with pilot training, there won't be any jobs for pilots anymore. If you're interested in flying airplanes, you might want to take on computer science so you can actually write programs and design computer systems that will fly airplanes. And she was just going like,
Yeah, it's
What?
kind of a bit of a shock.
But it's better to tell her now than later on that she realized, oh, you mean I'll just be flying transport airplanes or just be a backup on an airplane in case the computer system breaks down or something. Because it's happening. Okay, it's going to happen even sooner than cars because in the military that also saves money. Okay, it's also a good way for contractors to sell new things to well, guess what? Taxpayers. We are all paying for all that stuff, right?
There's less traffic too.
Yeah, but so they have the drone now, the X-47B, that is fully autonomous. Doesn't actually require someone to be remotely controlling it, which is a big step from the Predator drone, which typically requires someone to be flying it. But if you think about it, that's only the first stage. The second stage would be the refueling airplanes, right? The airplanes that are circulating, all the time. Because now, we have people flying those airplanes. Now, even assuming it has enough food and restrooms and also a place for people to rest, people cannot stay on an airplane for days. Okay, they just go cuckoo, right? It's just not a good thing to have. But computers, especially when the airplane itself is is full of fuel, to refuel other airplanes, it can potentially stay up there for what, days, weeks, I don't know. I mean, until it runs out of fuel itself, right? So if that airplane itself is autonomous, then you are saving a lot of money because you don't need to have people to fly those airplanes anymore.
It might actually be safer to refuel too.
Because it's more accurate. It can rely on more sensors instead of just a pair of eyes. Yep. So it's kind of interesting. This is really where things are going. Passenger airplanes will be next. Okay, because we have so many of those, and they have to retrofit existing passenger airplanes to make use of fully autonomous systems. For the most part, the hardware is already there. Okay, the radars, altitude, all the equipment. It's already there. It's just a matter of integrating what they have on the airplane electronically to a control system and making sure the control system is reliable. They will always have a pilot too.
Yeah, actually it's just a pilot is only used for basic inputs for the very last percentage of landing a plane. People don't realize it's almost an autonomous system already. It's just the pilot is used for the very ending of landing a flight.
Yeah, but even that part, I think they can probably do it autonomously as well. If not now, probably in the near future, it can be reliably done.
Yeah.
Yep. So things are all going that way. So what are we gonna do? If
Play
robots are
video
running
games.
everything.
What did they do to Baxter?
With
What did
Baxter?
yeah, what did they upgrade on?
Well, it says faster, smoother, and much more useful. I guess you can read it on your own and find out. Yeah, Baxter has a face, which is kind of interesting. Is that from MIT, from Rodney Brooks' lab?
I think it's MIT, yeah.
Yeah, I think it's Rethink. Okay, let's play this. No voice, no sound.
It's supposed to make them do like industrial jobs or something.
I like the squinty eyes. Not squinty anymore.
Like he's actually looking over there.
Yep. Trained by demonstration. So the arms have have encoders, so you can move it and it can record the motion. But this is still rote learning, though. I mean, unless it has a really good learning engine that can generalize, it's still really rote learning. It's cool. But it's really an early step to automated manufacturing.
That's cool.
If you think about safety, this is nothing compared to a circular saw that's running at several thousand RPM. And these days they have circular saws that have a touch sensor. So if the circular saw is about to cut a finger, it will detect the contact of a finger and break it in time to avoid the actual accident.
Called saw stop.
Yep.
It uses like a metal brake that the saw
Yep.
actually cuts into, and then he just uses
It just stops
centrifugal force and
immediately.
pulls it down.
Yeah, isn't that amazing? I mean, yeah, it's expensive. I mean, every time you actuate that thing, it will cost quite a bit of money to replace it.
Better than
Yeah, but the health and safety costs that are
Right.
avoided.
It's
are-
definitely offsetting that part. Yep. So, robotics, it's coming. It's going to be here. And it's already here, in some cases. It's just a matter of, I think that the software is the threat, is the limitation. That's really the threshold of how much we can do with robots. Yep.
Well, that's cool and all, and I like the thing that you can work around it without a cage, because the manufacturing robots that we have now, if you're
You don't
anywhere
want
near
it
them,
here.
they'll take you out.
Oh, they would take out a lot of
Yeah.
things. Yeah.
But a big problem is when you give them the capability to make decisions, who is responsible for that when they make a mistake?
When they make a mistake, it will be, there'll be a long chain of, people, or people who are involved. So you have the manufacturer of the robot, who wrote the firmware, and then you have the people at the factory who are actually doing the training or the customization of the robot. So there'll be a lot of people involved, in the process, and the liability would be kind of difficult to determine unless someone is actually technical enough in the field to make that determination. And that really brings up another thing, which is, if you are technical on one hand and you get a JD on the other hand, you don't have to worry about not having a job. Because do you know what a JD is? A lawyer. Okay, it's I cannot remember the name. It's judicial something doctorate. Okay, JD. Okay. Juris Doctor, that's it, okay? But basically, every lawyer is a JD, okay? So if you get a JD, which is, a degree, kind of like a Doctor of Philosophy, a PhD, except this one, is more on the law side. If you combine technical knowledge like electrical engineering, electronic engineering, computer, engineering and stuff like that with a JD, that's a really, really good, lucrative combination. Because there are very, very few of those. Okay, you have really good top-notch, engineers, scientists, and whatnot. You have really good lawyers, but there are very few that can do both at the same time. And those people will stand to make a lot of money. All right, and a lot of paperwork too. So that's basically what I want to show you guys a little bit. And also right after this class today at noontime, I'm going over to room 152, section D and section E, because the Dev Club is now active. So there will be a club meeting today, and the club president is going to bring over this for today. So for those of you who are interested, you can definitely go. It's called a Sumo bot. It's kind of like a sumo robot, except it's called Zumo. And I might have misspelled it too. There we go. So this is just the chassis, but he has both the electronics and also the chassis. And today we're gonna, try to figure out how to get these things, programmed. I know these are not the same kind of robot that we just saw earlier, but we have to start somewhere. So that's what we'll do today at about noontime over at room 152, section D and section E. So for those of you who have time and you're interested, you can definitely go with me over there. Yep.
So is this a cheaper way of building a little robot?
The fully assembled version is about $200, but that's including the chassis, all the mechanical parts, and also the electronics. It's C programmable, C++ programmable, which means in your next class, in your C++ class, you'll be learning how to write programs in C++. You can definitely apply those skills to robot programming, to something like that. So it's something for you guys to think about. I know $200 is not, chump change, but at the same time, I think it's reasonably good investment, in this case, especially if you just join the club and play with the one, over at the club, that's actually not a bad idea. Right, so getting back to our class, the first thing I would do is I would go over the solution of the previous homework assignment, which is named More Nested. And then the next thing I'll do, sorry, that was me. And then the next thing we'll do is to look at the new homework assignment. This is the old homework assignment that was due last week, and I finished grading it already. So we'll go ahead and take a look at this homework here. Okay, so we'll open up the document.
Did you want to roll sheet?
Row sheet. And I'm pretty sure it's right here. Thank you. Thanks for the reminder. There we go. Okay. So now we have the document open, the algorithm on one side, and then we'll open up the trace on the other side. Are there any general questions about this homework before I get started here? No questions? Okay. As I go through this, I can also point out, what are the most common mistakes with this one. A lot of people got it 100% correct, but there was one common mistake that many people, also made. So I'll go over that when we get to that point. Okay. So let's go ahead and get to tracing. Line 1 doesn't do a whole lot. It is the beginning of a while loop, a pre-checking loop. So we have to confirm the condition here. X is greater than or equal to y is true because 64 is greater than or equal to 2. Then we move on to line 2. Line 2 is inside the while loop. Okay, this is one of the two statements inside the while loop. Okay, because right inside the while loop we have two statements. The first statement is a conditional statement that spans from line 2 to line 6. The second statement is line 7. A lot of people miss line 7 as a statement right after the conditional statement. Okay, so we'll see what happens, after we get the conditional statement done. But I just want to point out, a very common mistake in this particular case. So line 2 is the beginning of a conditional statement. We have to evaluate the condition of the conditional statement. X is greater than or equal to 16 is true. So we move on to line 3 so that we go to the branch that corresponds to the condition being true. Line 3 is going to divide x by 2 and then store it back into x. So x will be updated to 32. Okay, so here is what most many people made this mistake at this point. Where am I supposed to go now? I'm done with the conditional statement. When I'm done with the conditional statement, I have to continue with whatever is after the conditional statement, if there's one. There is line 7. Okay? Line 7 is not a part of the conditional statement. It is after the conditional statement. So many people miss this part here to increment the value of z by 1. Okay? I'm not taking a whole lot of points off, but that really is important to make sure that we understand, how one statement is following another one. After line 7, then we can go back to line 1 to the beginning of the pre-checking loop here, and x is greater than or equal to y is still true because 32 is still greater than or equal to 2. We go to line 2 again, x is greater than 16 is still true. We go back to line 3, then we update x to 16 this time because it's halving it each time. Then we also have to go to line 7 to increment z. Z goes from 1 to 2, and then we go back to line 1 again. X is greater than or equal to y is true because 16 is greater than or equal to 2. We go to line 2. X is greater than or equal to 16 is true for the last time because 16 is greater than or equal to 16. We go to line 3. X is now halved another time, from 16 to 8. Then we go to line 7 again. Z gets incremented to 3. We go back to line 1. X is greater than or equal to y. It's still true because 8 is greater than or equal to 2. But this time when we go to line 2, x is greater than or equal to 16 is false. Then where do we go?
5.
We go to line 5. Very good. So we double the value of y instead. So y gets a value of 4. And then where do we go? We go to line 7 because line 5 is the last line of the else branch of the conditional statement. When we are done with line 5, we get out of the conditional statement completely, but there's one statement after the conditional statement, which is line 7. So line 7 is something that we have to do regardless of which branch we take in the conditional statement. So now it's incremented to 4. We go back to line 1. Basically the same thing, and I saw quite a few people doing this, doing the copy and paste within a document. That's perfectly fine. I mean, why retype something when you can just copy and paste and you still get pretty much the same result, right? So here's line 2. We go to line 5. It doubles the value again. Yep.
So you're fine with us copying our own work, right?
Absolutely.
Okay.
Yep. So because I can tell where it is coming from. And typically something like this, would not stand out because I would just have like 4 or 5 entries, of the same timestamp. It's not an issue. It's only when almost the entire document just appears out of thin air. Then it'll go like, okay, where did that come from? Okay, so we have one more iteration here. So we can even do something like this. I pressed the wrong key.
Control up.
Control up. Okay, there we go. And paste it here. Yep, there we go. So this will basically put 8 entries into the log. On line 5, we have it again from. We double again from 8 to 16. And then on line 7, we bump it up to 6. Now this is also another interesting place. I did not expect this at all, but quite a few people did not go straight back to line 1, and instead went to like line 2 again at this point. But it really needs to go back to line 1 in order to re-evaluate x is greater than or equal to y. This time it is false because 8 is not greater than or equal to 16. So once that is determined to be false, then we get a post and the trace is done. Yep.
If we left off that last x is greater than or equal to y is false, so take off.
You get one. Yeah, I take off 1 point. Because the whole assignment is 10 points. But it really is important to remember that you cannot exit a loop unless you re-evaluate the condition.
Okay.
Yep. So it's not a major point take off, but it is important. All right. So that's the trace for the previous homework assignment. I'm gonna You don't even know why I bothered to save it. And are there any questions about the trace? No questions about the trace? All right. So we'll go ahead and get started with the new homework assignment, and it is called pre-post assignment. And we'll take a look at the assignment, and then we'll go ahead and take a look at today's topic. So this one is about the same thing. Right-click and download the file. Basically, the whole sentence is a hyperlink. And then we save it, and then we open the document. Okay, so this is a regular word processing document like this one. And what you are going to do is to work out the pre and post conditions. And remember, working out pre and post condition is not the same as tracing. Okay, so I don't want anyone to plug in specific values to trace the algorithm, because there's no way to trace this particular algorithm. The precondition is x equals m and y equals n. Okay, and I'm not even telling you what is m or what is n. So there's no way this can be traced because you don't know which branch it's going to take. But yet, the end result of the post condition of this whole thing actually has a meaning. Okay, it actually accomplishes something that is important. Okay, I'm not going to tell you what it is, because you're going to derive the post condition and you'll figure out what it is. The second one, there are two questions in the same question sheet. The second one is about the same. We have if x is less than 0, then we have x gets negative x, else there's nothing to do, and end if, and that's and that there we have the entire statement. So in both examples, I have an else, but there's no statement corresponding to else. In other words, you can look at line 6 of the first algorithm and line 4 of the second algorithm as a null statement. Okay, it's a statement that doesn't do anything. So with a statement that doesn't do anything, how do you derive the post condition? It's the same as the precondition because it doesn't do anything. Okay, so in both of these cases, now I'm just giving you, that part of your homework assignment. In the first one, you just say post 6 equals pre 6 because it's a null statement. Nothing is done on that line. In the second one, you just say post 4 equals pre 4 because it's a null statement. That's all you have to do because they are basically null statements. The only reason why I put this in is because if I don't put this in, I could have given you this instead, right? Because it means exactly the same thing. It doesn't have an else branch, which means when the condition is false, there's nothing to do. But it's a little bit harder to keep track of things this way because you do have to keep track of the else branch to figure out what condition will get you to the else branch. Yep?
So are we supposed to, for the show, where we show our work, are we supposed to have pre and post for every line?
Yep. Well, except for there's no post 1 and there's no post 5. So those two lines do not have post conditions. There's only pre 2 and there's pre 6 as well, because pre 6 indicates why are we following that branch, basically. Okay.
So for line after the 1, we'll say the post will be pre 1. Is that what, or do we just don't write anything?
Okay, let's go ahead and do some examples and see if my examples today can answer your question. Okay. We actually addressed that several times already, so if you kind of watched the YouTube from last week, that actually will help answer that question as well. So I'm going to leave this one up for now, and then we'll work on some examples. Okay, so I'll work on some fairly senseless examples. So we'll have x, if x equals to 10 is a magic value, then we'll do something about it. So in this case, x gets x times 2. On line 3, we have else, and then we have line 4 here, and we'll do something about y. Okay, y gets x, and then on line 5 we have end if. Okay, so this particular pseudocode does not accomplish anything particularly meaningful. It's just it is what it is, and I want to illustrate what do you do in order to do your homework assignment. So it's really just for that purpose. And as a precondition of line 1, I would just say x is greater than z, another variable. and y is less than k. Okay, there we go. Okay. So now I have an algorithm. I have a precondition of the entire algorithm. I want to derive the post condition of the entire thing. Okay. So there are several things that we have to go through here. The first thing we'll do is to figure out what is pre-2 and what is pre-4. I do not have a post-1. The reason why there's no post-1 is because which line I execute after line 1 depends on the condition. So there's no such thing as a post-1 because I'm not always going to line 2. So post-1 splits to 2 different paths, and I cannot capture 2 different paths by one single post condition, and that's why there's no post-1. But there is pre-2 and there's pre-4, which basically means if I'm about to execute line 2, what does it mean? What has to be true? If I'm about to execute line 4, what does it mean? What has to be true? Are we doing okay so far with the meaning of pre-2 and pre-4, the preconditions of line 2 and line 4? Okay, so the precondition of line 2, now this is also something that you have to follow, the format you have to follow. It is based on pre-1 because by the time I get to line 2, whatever is in pre-1 still has to be true. I don't have a chance at this point to modify any of the variables, so that has to be true at this point. But on top of that, the condition of the conditional statement also has to be true because otherwise I would not be about to execute line 2. Are we doing okay so far with the rationale? Okay, so this is also what you have to do in your homework, is to start with this step here. And then the next one is to just copy and paste what is in pre-1. And because I give you a document, you can also do exactly the same thing. You can just copy and paste it. Like that. For those of you who want to say, hey, I can now resolve, the relationship between x and z because I know x is 10, so I can say 10 is greater than z and y is less than k. This part is optional, but you can certainly make that conclusion that z is less than 10 at this point. Okay, that's fine, not a problem. If you don't want to do this step here and just have this part as the answer, that's perfectly fine as well. Let's work with pre-4. Pre-4 is also based on pre-1 because if I'm about to execute line 4, that means the condition is false and I'm continuing from line 1 to line 4 right away. So pre-1 still has to be true because I haven't had a chance to change anything. The condition of the conditional statement has to be false because otherwise I would not be following the else branch. So the next step is really just to expand what we know about pre-1. And this is just saying x is not 10. And that's it. There's really not too many ways to simplify this, so I'll just leave that as it is. Are we doing okay at this point? Now obviously your answer to the 2 questions will be different because you have different conditions and different preconditions to the entire algorithm. But the structure of figuring out what is the precondition of the then branch and what is the precondition to the else branch should be the same. Okay, so that part should be common. What happens next is something that is really the core of today's lecture. Okay, so I'm going to leave this one as it is at this point. So this is my little bookmark here to basically say, let's go back to this point a little bit later. So what I want to do now is to focus on line 2 by itself. Okay, so this is line 2 all by itself, and we have a precondition of line 2 already. Okay, so the precondition of line 2 is 10 is greater than z, y is less than k, and x equals 10. Okay. The question now is, how do we derive the post condition of this line here? What do you think? Have I started to talk about function and the inverse function in this class?
No.
No? Not really? Okay. So let's go ahead and do that part. Okay. So what we'll do is we'll say, instead of just doing it in an intuitive way, we'll try to figure out a very mechanical way of doing this. Okay. So what I'll do is I'm going to say the right hand side of line 2 is f of x equals 2x. or if you want to spell it out, it's the same thing as x times 2. Okay? So what this is really saying is I'm just giving the right-hand side of line 2 a name. It's called the function f of x. And it's defined to be whatever is on the right-hand side of line 2, which is x times 2. Are we doing okay so far with the function, the concept of using a function? It's really just a name. Okay, you copy the entire right-hand side and you call it a different name. Are we okay? All right. The next part is the kind of really the tricky part. F of x has an inverse, and in using a plain text editor, I'm just going to use f prime to indicate the inverse function, because it really should be f to the power of -1, or superscript -1 to indicate the inverse function. What do you think is an inverse function of 2x? X divided by 2 or x times 0.5. Okay, either way, it's basically saying the same thing. So f of x, f prime of x, the inverse function is now x divided by 2. Okay, so maybe I should slow down here and talk a little bit about what is an inverse function and why it is important in this case. Okay. The best way to illustrate it is to use a graph to illustrate what is an inverse function. In this case, we have x here, and then we have f of x here. In other words, if I can put a dot that corresponds to f of x, let's say this is a dot that is corresponding to that, what it means is this x value is mapping to this f of x value. Okay? In other words, it's a map. Okay? F of x is really a map to say what value of x will map to what other value of f of x. They can be the same, they can be different, but in this case, it's really easy, right? If I plot a line of y equals to 2x, it will look like a linear line like that, right? So I'll just give you a few questions. Okay? If at this point here, x has a value of, let's say, 3, what do you think it will map to as f of x? 6, right? Because f of 3 is 2 times 3, and it has a value of 6. Is that okay? And over here, maybe we have 5 over here, and that will map to
10.
A value of 10. Okay, so that's the feature. That's how we use a function. It's a map. It goes from x to the y-axis, basically. Are we doing okay so far?
Yeah.
Okay. Can we do it the other way around? In other words, if I say over here we have 12, can we figure out what it maps back onto the x-axis? What is it?
6.
Should map back to 6. Now, how do we know it's 6? Algebra. It's algebra, right? Because it's f of x is 2x. The inverse function is x divided by 2, and that's how we can start with f of x and reverse it back to x. That's the feature of a inverse function. Okay, you can go one way, that's the function itself, but when you go the opposite way, it is an inverse function. Okay. So getting back to this example here, now you don't have to do this step here, but I can prove to you that if you apply the f of prime to x and then you apply f on top of the whole thing, what should I get back? I should get x back, right? Because the f and f prime are supposed to cancel out each other. Okay, so let's see whether that really is the case or not. Okay, this is a question. And can someone remind me again what is f prime again? What does f prime do to x? Divided by 2. Okay, so that's the first step. And then what does f do to whatever is inside the parentheses? It doubles it, right? So we end up with this expression here. And by rearranging things a little bit, I can simplify that to x. I'm not going to go through the algebra to do that simplification, but I think most of you can see the 2 cancels out the divide by 2, right? Okay, so that's the feature. That's how an inverse function works. All right, so the bottom line is, in this case, on line 2, the right-hand side has an inverse function. That's the bottom line. Because when that is the case, we can apply a very mechanical step so that we can go from the precondition to the post condition. All right? So what we'll do is to explain that this is why we can use the substitution operation, or in the notes it's called the substitution rule, okay? And this is really, really mechanical, because what it says is the post condition of line 2 is based on the precondition of line 2, but we have to do something about it. Every time you see the variable on the left-hand side, in this case it is x, you replace that in the precondition of line 2 with f prime, the inverse function, applied to x. Okay, so let me just highlight this little part here and explain once again here what it means. The first component is pre2, and pre2 is what we are starting off with. Okay, that's the precondition of line 2. The second component is x, which is telling us what are we looking for inside the precondition. The third component is f prime of x, which is what are we replacing x with. Are we doing okay so far? So again, I'll just highlight the individual parts. What are we starting with? Okay, look at this as a document, okay? This is what we are searching for. We are looking for the variable on the left-hand side of the assignment statement. This is what we are replacing it with, which is the inverse function of f applied to x. The
Right.
next step, yep, go ahead.
I still don't get why we're replacing it with the inverse function.
It'll be clear, okay? Yes, but that's a good question. Okay, keep that in mind. But just kind of keep observing this, and then we'll get back to what you asked. So if we just mechanically do this, we can just go ahead and copy what is the entire precondition of line 2, and this is x, and f prime of x is here. It is the inverse function of whatever that will undo the effect of line 2 in this case. And then the third line is the actual application. Now the actual application goes like this. Okay, you just take the entire expression like this and you say, is there any occurrences of x here? No. Okay, so there's nothing to be done here. How about this one? No. How about this one here? Okay, so we'll go ahead and just blindly replace x with x divided by 2. And for those of you who want to do your algebra a little bit and simplify this, you can see that I can multiply both sides by 2, so x divided by 2 becomes x, 10 becomes 20, and that's my answer. Does that make any sense? If you look at the precondition of line 2, which is, I know something about z, it is less than z. I know something about y and k, y is less than k, and I also know something about x, it is equal to 10. Okay, and that's prior to the execution of line 2. Yes, go ahead.
Sorry, are you still going with the post 2? Aren't we going to change the 10 that's greater than z?
10 is greater than z is not affected because the assignment statement does not impact z at all.
Well, the thing is, before you said we could have kept it as x is greater than z, right?
Correct.
We didn't have to change it. But then don't we substitute every x in there? Or
Right.
The other is inverse.
Yeah, we could have substituted, if we did not substitute this with x, if we did not change this to 10, then it would still be okay because it would become x divided by 2 is greater than z. But x would be 20 by that time, so it would still be okay, it's just not as clear. But it is nice to perform that step earlier than it is, but it comes to the same conclusion. Yep.
So that's just a really complicated way of doubling x.
Kind of. Kind of. But that's not the only reason why we are doing this, okay? Because the function and the inverse function may not be as simple as just doubling or adding 1 and subtracting 1. This works for anything that has an inverse function.
Allows you to do more complicated things.
Right, but the most important part is it is really just an application of a rule, right? Okay, if you look at the right-hand side, it becomes a function of the left-hand side, okay? And if that function has an inverse function, you can just blindly use the substitution rule and be done with it. You can go from the precondition to the post-condition without actually having to think the whole thing through. All you have to do is to find the inverse function. Okay. So this is the conclusion here. Okay, this is all I expect you guys to do is just to say that x divided by 2 is 10. But for most of you, if you want to do the extra step to say x equals to 20, that's even better. But it's not required. All right. So are there any questions about this step here? This is what I want. Yep, go ahead.
I just have a question about the precondition number 1, the first question. You wrote like x greater than z, and the question is not z. Okay.
I don't know. Okay, so that's the whole thing about pre and post condition is it's just telling you how a variable relates to other things, constants or other variables. But it doesn't have to tell you the exact value of anything. So in this case, what pre1 is telling you is x is greater than z. This is how I know how the two variables relate. And y is less than k.
You go up, you see no z. Like.
That's right. Z may be something that I use after line 5. This may not be the entire algorithm. There may be additional parts of this algorithm that depends on Z. So the precondition can include variables that is not even mentioned in the part of the algorithm that I'm giving you, or not everything can appear, in the precondition. Like in your homework assignment, in one of them, I just have true as the precondition, which means I'm not telling you anything about how the variables relate to each other at all. But you will still have to come up with a conclusion and say, oh, okay, so even though I don't know anything about the variables before line 1, but because of the structure of the pseudocode of the algorithm, I can still come to the conclusion that when the algorithm is done, this has to be true. This is how the variables must relate to each other. And that really kind of goes back to the previous lecture from last week. Remember last week what we did? We proved the algorithm defines the maximum of 2 variables to be correct. So that really brings us back to that, right? Because the precondition is just true. I don't know anything about x, y, or z. But yet, because of the derivation, we can come to the conclusion that z effectively is the maximum of x and y. But that's because of the structure of the code and also the way we do the pre and post condition derivations. Are we doing okay so far? Okay. Well, that's why we are doing some of these examples so that I can give you some examples of what to do when you encounter cases like that. Yep.
So could it be said as line 2 contains the function, pre2 has the inverse function, and then post2 is the function being performed on the inverse function?
It's not, well, okay, the way I look at this is to say in the precondition, okay, so I'll just go ahead and highlight the parts that I think are important. So it's basically what it's saying is in the precondition of line 2, I know how x relates to, in this case, just a constant of 10, okay? And that's before line 2 executes, okay? So what I want to do is to say, but I don't want to get rid of what I know about x. I want to keep as much information about my variables as possible. That's what I want to do. When you look at line 2, I also know what it is going to do to x. Okay, that's basically what it's going to do to x is to double the value of x, right? So the question now is, looking at the value of x after line 2, can I reverse it back to the value before, so then I can keep the relationships that I have already established before line 2 executes? That is why we apply the inverse function. Am I doing okay so far here? Okay, so if I just go back to here, okay, if you look at this part here, which is the only part that got modified, this is really saying this x is already referring to the value of x right after line 2 executes. Divided it by 2 is reversing the value of x after line 2 to the value of x before line 2. did we know anything about the value of x before line 2, how it relates to other things? We knew that it equals to 10, right? That's basically what it's saying. Okay, if I reverse the effect of line 2 to x, that value, the reversed value, will still be equal to 10. Is that okay? All right. I'll give you another example to illustrate this point. Okay, what about line 4? Okay, line 4 is a little bit different. Okay, so what I'll do is I'm going to repeat the actual line 4 here. And also the precondition of line 4 is already known. It's because of the structure of the code again. And we'll just get rid of this stuff here and just focus on pre-4 here. All right. So in this case, the right-hand side of line 4 is f of y, because remember, it is a function of y. It is function of whatever variable is on the left-hand side. But the function itself is x. What does that mean? I mean, that seems kind of awkward. Can we draw a picture of this? Let's take a look. So this time, if I draw this picture, on one side we have y, okay, because that's the variable inside the function itself. And on the usual y-axis, we'll just call it the vertical axis, we have f of y. Okay, if I say at that particular point x is here, okay, so x has this value here, what do you think is the shape of the line corresponding to f of y equals to x? Let me give you another question. What is f of 1? Okay, in other words, y is here. What is f of y? It's over there, right? What happens when y is over here? What is f of y? Does f of y depend on y at all? No, it does not, right? What does it depend on? The value of x. So if x is the same, stays the same, then we're looking at a straight line. It's a horizontal line. It maps every value of y to a single value, which is x, at the time when line 4 executes. Are we doing okay so far? So we are mapping an infinite number of values of y to a single value, which is x. So here's the opposite question. If I tell you that after line 4 executes, y has a value of something, can I reverse and say, well, knowing the value of y is blah after line 4, this has to be the value of y before line 4. Can I make that reverse? Is it a reversible kind of thing? It's not reversible. It's not reversible for one very simple reason. Everything maps to this point, right? So if I start with this point here, can I know where I came from? No, and that's why it's not reversible. Because it is not a one-to-one correspondence. Any function that maps multiple value to a single value, like this one, is not reversible. Or in math term, it does not have an inverse function. Okay? So what does it mean to us? Well, the simple way to say this is to basically say if the right-hand side does not refer to the variable on the left-hand side, it is not reversible. That's the simplest way to put it.
Can you say that again?
Absolutely. If the right-hand side of an assignment statement does not even mention the variable on the left-hand side, then it is not reversible. The operation itself is not reversible. If I know the value of y after line 4, there's no way for me to know the value of y before line 4. Because it just overrode it. But the new value does not depend on the old value of y at all, so there's no way for me to reverse the operation. So in the explanation here, I can just say, because f of y does not rely on y, f of y has no inverse. Now, because f of y has no inverse, we apply the forget operation. This is the other way to do it, okay? Which is not preferred because, in this case, I'm going to lose something, but I have to lose something because there's no way for me to keep it around, okay? All right, so the application of the forget operation is really just to forget something. The post condition of line 4 is based on the precondition of line 4, but we have to do something about it first. We have to say we are forgetting certain things in the precondition of line 4. Anything that mentions y, we have to forget, because the relationship between y and whatever in the precondition is no longer guaranteed in the post condition. Is that making any sense? Okay. It's not guaranteed. It may still hold, but the chance that it may not hold means that we cannot rely on it, and so we have to get rid of it. But there's one extra thing we can say, because now we know for sure that x and y have exactly the same value, because that's the effect of the assignment statement. It makes the value of y the same as x in this case. Is that okay so far? Okay. So this is the template. The template will expand because we already know what is pre-for. So I just copy and paste the entire pre-for into the first part of the forget operator. And then we can just go ahead and perform the forget operation. To perform the forget operation is really just looking at the entire expression here. And then we say, okay, can we keep this one around? Does it mention anything about y? It doesn't mention anything about y, so we can keep it. Does this mentioning anything about y? Yes. Yep, so we have to get rid of it, because once we change y, this relationship can no longer be guaranteed. What about the last one here? Does it mention anything about y?
No.
Nope, so we get to keep it too. And then we add whatever is the last one here, because this conjunction here is after the entire forget operation. So that is one additional thing that we're adding to the post condition of line 4. And that's what I expect you to do, is to basically just to state post 4 is x is greater than z, x is not 10, and y equals to x. In this case, I don't know exactly what x is, but I just know that at this particular point, right after line 4 executes, I know y and x have exactly the same value. Are we doing okay so far with this? Okay, so I have already illustrated the two operations that you can apply to an assignment statement. One is the substitution operation, which you apply when there's an inverse function, and the other one is a forget operation when you cannot find an inverse. And typically when the right-hand side does not refer to the left-hand side, that's enough, and you just say, okay, we have to apply the forget operation. All right, so now back to where we left off here. Okay, so now we have post 4 and pre-4, post 4 and post 2. What is post 5? Just take a look at the code here. This we have done already on the other day. This is a conditional statement. I know the end result of the entire then branch being post 2. I know the end result of the entire else branch being post 4. I am now at the point where the two paths would merge. So what can I say right when they merge? Post 2 or post 4, but without the either.
Yeah.
Okay, it is very important to say without the either. So it's post 5 is post 2 or post 4. Without the either is not an exclusive or. And the next step is really just to expand what we are talking about here. So we have post 2 being this guy here. Just copy and paste. And you can do copy and paste too, because you're going to use a word processor to work on this homework assignment. So for this particular question, that is the entire answer. any questions about this?
Can you repeat what that last part was, where you said what was very important to consider? You said after the or part, post 2 or post 4, and then you said something else at the end of it, which is very important to consider. I couldn't quite hear that part.
It's without the either. It's not an exclusive or. In other words, there's no guarantee. In this case, it is kind of exclusive because one side says x is 20 and the other, well, no, there's no guarantee. They can. Let's see, can they both be true at the same time? I suppose both of these can be true at the same time, so there's no guarantee that only one can be true. When we use the word either, it implies only one of the following can be true. Okay. Right? So in other words, if I say either John or Mary can get an A in this class, what does that mean?
Only one of them can.
Yeah, it's Highlander, right? There can only be one.
Right. So is there any way we can write that? Is there any way we can specify that? Like there's
Yes.
IFF, but I don't know.
Right. If you want to, now, this is the wrong place to put it, okay? But I'm just saying that if you want to say it's exclusive or, in logic it is called EOR, E for exclusive.
Okay.
In computer science, it's typically using an X for exclusive. So so it depends on whether you're a math person, then you use the E. If you're a computer science person, you use the X. But that's how you express, only one and only one can be true.
Okay.
There's no symbol for that?
Huh?
There's no symbol for
There
that?
is a symbol for that. The symbol is also very confusing because it looks like it's a plus with a circle around it. Because in logic expression, especially when you're dealing with computer engineering and gate logic, the plus symbol is often used to represent disjunction or. Okay. In other words, or has several ways to express it. One way is just to spell out OR. One is the V symbol, and the other one is actually just the plus symbol. So in Boolean algebra, this is used a lot. Exclusive OR is a plus with a circle around it, but it's a different beast compared to just regular OR.
Yeah, that plus for disjunction would be confusing.
Well, plus for disjunction and then multiplication for conjunction. Because in Boolean algebra, what we usually do with multiplication, a lot of what we know about multiplication actually applies to conjunction in Boolean algebra. And a lot of what we know about addition also applies to disjunction. And that's why they borrowed those symbols from our usual arithmetics. And some of you, especially those of you who would major in mathematics, will have to take a class called abstract algebra. Okay, has anyone taken that class already?
What is X equals Y?
Is anyone looking forward to taking that class? That is one class where you will just have to keep in mind, whatever you do, whatever you learn, keep in mind that 1 is not 1, 0 is not 0, plus is not plus, and multiplication is not multiplication. They are merely symbols to represent certain things that have similar properties of what we know about multiplication, addition, 0, and 1.
What's that like? What would that be used? Was that like in quantum mechanics?
No, abstract algebra is really just a math class. It's one of what they call a gatekeeper class. Those who can pass, will have the potential to basically major in math and get a math degree.
Okay.
Those
So if you
who cannot pass that
yeah.
class probably should not have started as a math major. That's basically the cruel reality of classes like that. It's a divide. It basically is a gatekeeper to see who would be suitable for that. Exactly. Yeah. It's also a good class to train your thinking in logic and also in symbols in general. All right. So any questions at this point? what exactly is algebra? Why are we dealing with algebra so much? I mean, in science, all kinds of sciences and computers and math classes.
Guess it's fun.
Because it's fun. Has anyone taken linear algebra? Okay. In linear algebra, don't they have something that's similar to multiplication? And something that looks like addition? Something that looks like a 1? No, basically what is a 1? A 1 is an identity of multiplication. That's what it is. 1 times whatever is whatever. That's basically the identity of multiplication. What is 0? It's the identity of addition. Okay, 0 plus whatever is whatever. Okay, but what about subtraction and division? I mean, aren't those also important? Well, they're kind of important, but the way that we look at it from abstract algebra is they are inverses, basically. Okay, what are you talking about inverses, right? Okay, so we are talking about x times y here, right? What do we mean? What do we mean by inverse? Okay, the inverse means x times the inverse of multiplication. That gives you 1, right? So this is an inverse with respect to the identity and multiplication. That's basically how we look at it. And for the same reason, x plus, which is the operator that we're interested in, the negation of x is an inverse to get back to the identity. You start with something, you have an operator. This is what it takes to combine these two using this operator back to the identity. So this is not an abstract algebra class. I just want to give you some exposure of what is abstract algebra. It works out in normal arithmetics, but it also works out in a lot of the other types of logic too. Okay, so are we doing okay so far with the homework? We got about 10 more minutes. I'll give you some additional examples, okay? The conditional statement part, I don't think I have to give you any additional examples. So what I'll do is focus on inverse functions and stuff like that. So we'll go ahead and start with something a little bit more complicated, okay? Because somebody said, well, but we're just doubling something or we're just subtracting something. Let's work with something a little bit more complicated and see whether we can do this part here. Okay, so x is getting 2 times its previous value. Well, let's not even use concrete numbers. Let's use just symbols, okay? So it's m times x plus c, okay? That's a typical, linear equation. Okay, so what we'll do is we'll say pre2 is x equals some constant k. I don't know what it is. And we know that m is non-zero, because if it's 0, we're in trouble. And we also know that c is, okay, well, I'll just give you this part here. Okay, this is not required, but I will say something about c also. C is greater than 0. So the precondition of line 6, not 2, is something in this case that I just completely made up as the precondition. In other words, this is what we know right before line 6 executes. Okay? The question is, what can we say about the post condition of line 6? Well, what are we going to do? I want to keep as much of this as possible. In other words, I want to say, hey, if I can reverse the operation of line 6 and get back to the old value of x right before line 6, then this part would still be okay. Okay, something will still be equal to k because that's the previous value of x before line 6. It will still be the same as k, and then m is not 0 and c is greater than 0. That stuff has nothing to do with the modification of x, so we get to keep that part anyway. Okay. All right. So now the question is, the right-hand side of line 6 is f of x is m times x plus c. Is there an inverse function. What do you think? Okay, how do we reverse the operation? Because it looks kind of complicated this time, right? Because we have a multiplication that we have to apply first, and then we have the addition that we apply second. So how do we reverse something like that?
X minus divided by X.
Sorry, say again.
X minus divided by X.
Yep, you have to reverse the last operation first, which means we have to subtract the c first, and then we divide it by m. Okay? So in this case, there is an inverse function. The inverse function is f of x is x minus c, so you have to reverse the last operation first, which is the addition of c, and then you reverse the other operation, the first operation, which is multiplication by m, so that becomes the inverse function. Okay, now with that inverse function, that means we can apply which operation? The forget operation or the substitution operation? The substitution operation, because now it gives us something to substitute x with. Okay, so now we can say the post condition is based on the substitution of the precondition of line 6. We take whatever is the variable is on the left hand side, which in this case is x, and we replace it with f prime, the inverse function of x, the inverse function of f applied to x. And then the next step is really just to expand what we know about pre-6, which is this junk here. Substitute it over here, and then x is x. F prime of x we have already figured out to be here, so we just stick it here, and I think I need, oh, that's the right number of parentheses. And now we can just blindly perform the substitution. In other words, every time we see x here, we say, we now have to replace it. Okay, so we're going to replace this guy with the inverse function, which is x minus c, the whole thing divided by m. And I always put extra parentheses just to be sure that we know how they nest. M is not 0, c is greater than 0. That's my conclusion. Because what we are doing is we are taking this x, which is representing the value of x after line 6 executes. And then we say, hey, if we do all these operations to the x after line 6, we get back to the x, the value of x before line 6. Did we know anything about the value of x before line 6? Yeah, we do. We knew it was k. So now we can reverse the operation that we just applied to x, get back to its old value before line 6 executed, and say that equals to k. Are we doing okay so far? It's basically an undo, if you will. If the inverse function is an undo, it's basically saying if I undo the effect of line 6, then I can still say that equals k, because I knew that was k to begin with.
What would an application, like, what would this do? Is that kind of like resets it for something?
No, it just gives you an ability to go forward, because now I can start with a precondition of one line, get to the post condition of that line, which will feed into as the precondition of the following line, and if I continue this step, I can go from step 1 all the way to the last step of an algorithm. So this is one way to move forward one step at a time when you're going from the precondition of one entire algorithm to the bottom or the last line of an algorithm. Are we doing okay so far with this? Okay, now some people look at this and go, it's all symbols, it doesn't seem to make any sense. You can plug in values and see whether it makes sense or not. Okay, so the next thing we want to do is to say, okay, let's make this more concrete and see whether it still makes sense. Okay, now to make this more concrete, I'm going to copy and paste this entire thing here. And then what we'll do is, instead of saying m is different from 0, we'll give it a concrete value. We'll say m is 2. Instead of saying c is greater than 0, we'll give it a concrete value, c equals 3. Okay? And instead of saying x equals k, we'll give it also a concrete value. Let's say x equals 5. So now we'll see what happens and see whether the result makes any sense. What I am not changing is this equation here. Okay, so the right-hand side is still exactly the same as before. All I'm changing is the precondition. So instead of using abstract terms, like the other variables, I'm giving every single one a concrete value. Okay, so that means I have to make some changes to my precondition because the precondition is now changed. This part has changed, so that means this part also has to be changed because we just modify and make these terms more concrete, right? And the same thing applies to this. Okay. Well, but since we already know what x is, what are we really talking about here? Okay, we know what k is. Okay, sorry, I forgot about that one. So this is 5. This is 5. Okay, there we go. Now it makes more sense. Okay, so what are we going to do? In algebra, the first thing we can do is to say x minus c. We multiply both sides by m. What is m again? 2. M is 2. So I can cancel out the divide by 2 with the multiplication of 2 to the other side, which is now makes it 10, right? I'll do this one step at a time. And do we know what c is? C is 3, so that means I can add 3 to both sides, right? So that means x equals to 13 because I'm adding 3 on both sides. And equals 2, c equals 3. Does that make any sense?
No, not with the preconditions, because the precondition is x equals 5, and now the postcondition is x equals 13.
Yeah.
But m is 2 and c is 3. So after line 6 executes, I should have updated the value of x2 2 times 5 plus 3, which is 13.
So you meant for k to be an x in your precondition?
So say again?
If you read the precondition line, it says x equals 5. Did that mean to be k then, based on your calculations?
Well, this is stating right before line 6 executes that x has a value of 5. This is saying, after line 6 executes, that x has a value of 13. Does that make any sense? Yep, makes perfect sense. Okay? So this is the reason why we have the inverse function. It's because, once we locate the inverse function, the rest is simple. It's really just a matter of search and replace. You doing okay so far with that? Your homework doesn't involve anything this complicated.
I have a quick question.
Yep.
You're saying that the substitution when you first write post 6 sub, and then you put your statements in, that substitution is distributed to
Every
each of those?
occurrence.
Okay.
So
I just
that
want to make
means
sure I understand that.
yeah. So that means this component is going to replace every occurrence of x. So if x appears multiple times, each and every occurrence will be replaced.
Okay. I just want to make sure.
Okay.
Thank you.
All right. So get started with the homework as early as possible, so you guys can ask questions on Thursday.
When's it due?
It's due next Tuesday.
Can you email me a copy of that document?
Tuesday.
Can you email me a copy of that document? I've been having a lot of trouble grasping the algebra in general. It's like I understand algebra, I understand the logic. I'm just having trouble getting them together.
Okay, this is what I'll do. I'm not going to do this for you, but I'll do it for the whole class.
Okay, that would be great. No, that's fine. That's fine.
Okay, so I'm going to send the whole class this document.
Thank you, I appreciate it. It's I'm missing how it all fits together, and I get it in the stuff individually.
Sir,
Oh, thank you.
I have a question on the homework as well.
Okay.
So you know how you says after the else, what's it called? Like the else function?
After the else?
After else, there was nothing in that line.
With the homework?
Yeah.
With the homework.
I was
Null
just-
statement. N-U-L-L, null.
N-U-L. Oh,
Which means
I didn't know how to
nothing.
spell it.
Yeah.
It's one of those unfortunate
Somebody
things.
gave me
Uh-huh.
works.
It works?
Remember?
It doesn't
They
work?
wrote me.
Okay.
I had
But you got added, right?
Yes.
Yeah, I saw your name on Boston, so I know that you're
Okay.
added. So it's all good.
Battery?
Mhm.
This is, it's interesting that this is a
What happened
class
in a way
that
more
is
occurred than I ever would want to know.
Yeah, I had